always the case?
That is always the case when you have a homogeneous equilibrium and you have a solvent in excess.
Wait, how is this homogeneous if there's liquid in it?
Oh, aqueous means, you know, it dissolved in water.
So when would it not be homogeneous?
So supposing we had a gas and a liquid, or a solid and a liquid.
Okay, so but then aqueous can count.
Aqueous is considered liquid.
So to get aqueous and gas.
Then that would be heterogeneous.
Okay.
Okay? Okay, let's look at a heterogeneous equilibrium example. Let's look at calcium carbonate going to calcium oxide and carbon dioxide gas. We write out the equilibrium constant expression, the concentration of the products divided by the concentration of the reactants. I have a piece of calcium carbonate in my hand. So think about the concentration of calcium carbonate in this piece of chalk. Right? What is the concentration of calcium carbonate in this piece of chalk here? Same. Okay? Therefore, the concentration of calcium carbonate is a constant. It doesn't change. So we can incorporate that into the equilibrium constant expression, and we write a new equilibrium constant expression, K sub C, and we say that it is equal to the concentration of carbon dioxide. If we write it in terms of K sub P, it is going to be the partial pressure of carbon dioxide. So here is calcium carbonate and calcium oxide in equilibrium. There are different amounts of calcium carbonate and calcium oxide here. Yes, Kasi.
I understand like why the concentration is the same, but I don't understand how you get a constant out of that, or how you write it, how you go from that to the concentration of CO2.
Oh, because just as what I talked about for calcium carbonate, calcium oxide would also be a constant. The concentration would be a constant. So both of these are going to be constants. So we would subsume that into a new equilibrium constant expression, and it would be just equal to the concentration of carbon dioxide.
And we know that it's constant because
they are solids.
Okay. Okay.
Okay, so let's look at this example here. We have two containers identical to each other, different amounts of calcium carbonate and calcium oxide, but both of them are at the same temperature. What is the pressure of carbon dioxide in these two gases?
I have a question.
Yes.
So does that mean that the concentration of all solids will always, like, not each solid, the concentration of the solid will never change, or it changes phases?
Right.
Okay.
So what can you tell me about the partial pressure of carbon dioxide here compared to the partial pressure of carbon dioxide here? It's the same, because the equilibrium constant is the same, and the equilibrium constant is the partial pressure of carbon dioxide. So despite the fact that you have different amounts of calcium carbonate and calcium oxide, the partial pressure of carbon dioxide in these two containers is the same because the temperature is the same. So if Q is less than, so let's now move on to a different topic. How do we predict, given a chemical reaction, given the concentration of the reactants and products at a particular time, how do we predict which direction the reaction is going to proceed? What we do is we calculate Q and we compare Q to K. If Q is less than K, the system will go forward. Right?
Yes.
If Q is equal to K, the system is at equilibrium. If Q is greater than K, then the system will go backwards. How can we justify this? Let's go to this equation here that we derived in class 2 classes ago. Delta G naught reaction can be written as minus RT natural log of K. Therefore, this can be written as RT natural log of Q over K. If Q is less than K, what is this quantity going to be? If Q is less than K, what is this quantity going to be? Less than 1. Log of a number less than 1, negative, and therefore the reaction goes forward. Questions? Okay, let's look at an example. Let's look at butane going to isobutane. The equilibrium constant for this reaction at 25 degrees centigrade is 2.5. So therefore K sub C is equal to 2.5. Can you answer this question now, please? So what do you get for Q? 1.6. Therefore, the reaction goes forward. All right, let's summarize what we've talked about. If you have pure reactants, what is the value of delta G?
0. No, just 1.
Okay, can you talk to your neighbor, please? If you have pure reactants for this reaction here, okay, if you have pure reactants for my favorite reaction, A plus B going to C plus D, what is the value of delta G at that instant time t equals 0?
What do you mean by pure reactants?
So at the start, I have just A and B, no C or D. What is the value of delta G?
So Q0, which or is that 1?
Yeah. Cool. Yeah, domain problems.
And the answer is I'm not giving you that value. For arbitrary value of delta G naught, what is delta G if you have pure reactants? Negative what? Negative 1. It's not negative 1.
It's non-existent.
Can you be more specific than that?
Oh, pure reactants.
Negative what?
Infinity.
Negative infinity. Okay, so if you have pure reactants, what is this quantity going to be?
0.
This quantity is going to be 0. Okay, log of 0 is negative infinity. Okay, plot x versus natural log of x. What does this graph look like? What is this point here?
1.
1, 0. Okay? Questions? So at time t equals 0, if you have pure reactants, Q is going to be 0 and delta G is going to be minus infinity irrespective of the value of delta G naught reaction. Even if the reaction is very, very unfavorable, some amount of reactants are always going to form products. But the amount of product that's going to be formed at equilibrium is going to be very, very small if delta G naught reaction is a very large positive value.
Wait. I am confused. Are we using pressure?
It doesn't matter. You can use pressure or you can use concentrations.
So then why does it equal 0?
So if you have all reactants and no products, then the numerator is 0.
Okay. So you're not going to get any products.
No, that's not true.
Huh? What? Oh, the pressure is going to be 0. Wait, what?
Okay, we just said that log of 0 is minus infinity. So at time t equals 0, delta G reaction is going to be negative infinity.
No, but why is ln 0? I mean, why is, so you're saying that T, P, P, P is 0?
I'm saying that the numerator here is 0.
So the partial pressures of the products are 0.
Right. So therefore, this whole quantity is 0.
No, you're only doing reactants. You don't have any products.
Oh, you're saying pure reactants as in there aren't, okay. Got it.
Okay? I'm happy to answer each and every question. Neha?
Why is the partial pressure 0?
Oh, I'm just saying, if you start with pure reactants, it's a hypothetical question. Okay? which I have quite often used on exams. Questions? You can ask this of a lot of PhD chemists, and they will get this wrong. A very fundamental concept that is misunderstood by a lot of people. Very, very basic concept. Questions? All right, let's move on to another topic. What we're going to talk about is supposing we're given the equilibrium constant, and supposing we're given the initial concentrations of A, B, C, and D, what are the concentrations going to be of A, B, C, and D at equilibrium? Okay, there are 3 steps in doing this type of problems. The first step is to write the equilibrium concentrations in terms of the initial concentrations and a single unknown x, and x usually refers to the amount of the reactant that has reacted, and that will become clear very soon. We write the equilibrium constant expression knowing the value of k, we solve for x, and then knowing the value of x, we calculate the equilibrium concentration of all the species. All right, let's look at this question here. So H2 plus I2 going to 2HI gas. You have 0.5 moles of H2. So here's how you go about doing this. You create something called the ICE table. So I, C, E. You write the initial concentrations as 0.5, 0.5, and 0. That's what you're given. Now we assume that X amount of H2 reacted, and we don't know what X is, but if we know what X is, then we know the answer to this question. If X amount reacted, then the change here is minus X. So initial, change, equilibrium. Minus X. What's the change here?
Minus X.
Minus X. And the change other than N? I can't hear. Plus 2x. So at equilibrium, can I call on somebody randomly?
Yeah.
No.
All right, I won't. Okay. So at equilibrium, how much are we going to have of H2? 0.5 minus x, 0.5 minus x, and 2x. Okay, so what we have done is step 1. All right, now write the equilibrium constant expression in terms of the known values of K and X. So what is going to be in the numerator here?
2x. Wait, are we going to do it by mole? Is it 2x over 1? For like molarity? Because this isn't like moles, right? It seems like changes in molarity. That's something wrong.
What is in the numerator here?
2x squared.
2x.
Is it a problem that it's at 430?
That's an extraneous piece of information. Okay? You have to know what is pertinent and what is not pertinent to the problem.
I have a question though.
Yeah.
Say the volume was not 1 liter. You would
Then it will be a lot more arithmetic here that I don't want to, deal with. Okay? I made it 1 liter to make the arithmetic easy. Okay? So what's in the denominator?
0.5 minus x.
And that's going to be equal to
54.3.
Okay, you got to know how to be able to write these types of equations. Yes?
So
Here.
why is the denominator squared?
Why is the denominator squared? Yes, Tamara?
Because when you do it, you're taking both values of the reactants, and for the hydrogen you have 0.5 minus x, and for the iodine you have 0.5 minus x. And when you multiply these together, you get 0 minus x squared. So
Oh.
2 of them.
Questions? Yes, Eric.
So if they hadn't been the same, like 0.5 minus x, you're just multiplying the
Right.
reactant.
Right.
Okay.
Okay, how do we solve this problem?
Calculator.
Neither one is correct. No calculator, no math. It's very simple. How do you solve this?
Algebra.
What's the simple way to solve this question?
Isolate x.
Okay, calculator is one. The algebra, what does algebra mean, Tamara?
So I'd basically try and solve for x.
Right, and what is this type of equation called? A quadratic equation. And you could use the quadratic formula. Sorry?
Oh, nothing.
I didn't hear what you said, Eric.
Nothing. I just don't like that formula.
You don't like that formula. Okay, I have good news for you. You don't need that formula for this particular question. Why is that? Why don't I need the quadratic formula? Why don't I need a calculator for this question? Just for this question. I'm sorry?
Because you can take the square root.
Yeah, take the square root of both sides. And you convert a quadratic equation into a simple, whatever linear equation. Okay, so now we're ready to talk about Le Chatelier's principle. If an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. Okay? If you perturb a system at equilibrium, then the system reacts to oppose the perturbation that you caused. Okay, let's look at a simple demonstration. Adding water to the right. Wait. Okay, so we have a system at equilibrium. We're going to add water to the right.
Water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Let me do this again.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
So you initially have a system at equilibrium. You perturb that equilibrium by adding water to the right. The equilibrium opposes your change and moves the water from the right to the left. Okay, that's all you need to understand about the Chatelier's principle. Everything else just is a consequence of this very simple idea. Okay, so let's look at SO3 gas plus SO2 gas plus 1/2 O2 gas. We have a system at equilibrium. If you add 1 mole of SO3 gas to this system, what will happen? Qualitatively, will the reaction move to the left, to the right, or will it stay unchanged? The reaction will move to the right, because you increase the concentration here, the system will oppose that change and move to the right. Okay, so you will reach another equilibrium position, and you can see that here. The number of moles of SO3 at the first equilibrium was 0.68. You added 1 mole, so at the time, the instant that you added, you had 1.68 moles of SO3. But the system evolves and reaches equilibrium, ends up with 1.46 moles of SO3. That's consistent with the Le Chatelier's principle. That's the qualitative prediction. If I were to look at the equilibrium constant here and the equilibrium constant here, if I take the ratios here and here, what will I get? Can you talk to your neighbor, please?
Well, obviously the equilibrium will shift, but whether it goes to reaction to product, so this
what happens to the equilibrium constant because of the addition of the SO3? In one voice, nothing. It stays the same. Okay, you reach a new equilibrium position, but the equilibrium constant remains unchanged. Yes?
Does K like change temporarily for like a tiny time?
No, because what changes is Q,
Oh yeah.
not K. K is only at equilibrium. All right, let's go to what happens when you change the volume or pressure. So let's look at NO2 gas. All right, let's look at this movie here.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
Okay, let me explain that again. So what you're doing here, you have a system at equilibrium. You increase the pressure on this system, and the system opposes that increase in pressure. And the way it can oppose that increase in pressure is by going forward, because by going forward it decreases the number of molecules. The pressure is directly proportional to the number of molecules. So if you increase the pressure on this system, then the system adjusts by going forward.
Is decreasing pressure considered a stress?
Absolutely. So increasing or decreasing pressure is going to be a stress. Let's look at this example here. Let's look at what happens if you change the temperature. Is this an exothermic or an endothermic reaction? Exothermic, because heat is being given out. So if you increase the temperature, if you put in heat, will the system go to the right or to the left? It will go to the left. Okay? What happens to the equilibrium constant? What happens to the equilibrium position? We just said that the equilibrium position goes to the left. What happens to the equilibrium constant? It's the equilibrium constant is dependent on temperature. It changes. And we remember we plotted log of K versus 1 over T. And for an exothermic reaction, the slope is minus delta H naught over R. Delta H naught is negative, therefore the slope is positive. So if you increase the temperature, what happens to the equilibrium constant? It decreases. Let's look at our final example. If you add a catalyst, what happens to the equilibrium position? What happens to the equilibrium constant?
The constant doesn't change.
The constant does not change. Why does it not change?
Because the catalyst doesn't change. It just changes the rate. Yeah.
The catalyst changes the rate of achieving equilibrium. The equilibrium constant, remember, depends only on temperature. Okay, so the equilibrium constant doesn't change, the equilibrium position also doesn't change. And what a catalyst does is merely reduce the activation energy between the reactants and the products. It speeds up the chemical reaction, equilibrium is reached quicker, but the equilibrium position and the equilibrium constant remain unchanged. Okay, we will stop here. You will have your quiz tomorrow, quiz 7. I will post assignment 8, review 8. I've already posted MCQ 8. I've already given it to you. We will work on that tomorrow. Yes? I think 19 and 20. Yeah, 21 and 22 are for lecture, for quiz 8. 19 and 20. Okay, fine. If you can find the original email and send it to me, that would be really nice. Friday, during office hours? 10 to 11?